So what we're going to be doing in this video is going over a few more example problems of using the Navier-Stokes equation to predict what flows are going to look like. The first example that we looked at was flow between parallel plates, a really simple flow profile where the flow is driven by the motion of the top plate. So we've described this before. What we did is we took a simple picture of the flow shown up here. We described the boundary conditions, the things that we know are happening. Often that's the no-slip condition, but we'll run into another boundary condition that's fairly common here in a minute. Things that we know that are happening at the edges of the flow, the boundaries of the flow. So we know it's no-slip condition at the bottom and no-slip condition there at the top. Then here we've taken a list of things that we can say about this flow profile, and we've used them to cross out different terms in the Navier-Stokes equations up above. This gave us a simplified Navier-Stokes equation, really simplified, only have one term left, along with two boundary conditions, and then the actual solution of this becomes simply a math problem. So this is the math problem. We start with this simple second order derivative, the simplest one that there is. We can solve that by integrating twice. We get two constants of integration and this nice linear function. We then get our boundary conditions involved. Our boundary conditions, right? Boundary condition 1 and boundary condition 2. And these are what are describing our two constants, C1 and C2. These constants get plugged back into our original function, our linear function, and this leaves us with the described flow profile. So that's the process. What we're going to do next is another example of a little bit more complicated flow profile. So what I've done is already drawn out what we're going to be looking at. We're going to be looking at the pressure-driven flow between parallel plates. So we still have parallel plates. We still have nice, easy Cartesian coordinates. We have now a high pressure here on the left side, and we have a low pressure here on the right side. So that pressure gradient is going to be what's driving our flow. It's pressure-driven flow. We still know the no-slip condition has to be true. So we have a boundary condition at the top and the bottom. That's fluid's not going to be moving at those positions. Because we know these things, we can kind of draw out actually what the flow looks like. We wouldn't have to do this, but it's always nice to know what the answer should look like. It's going to have to be 0 at the walls, and it's going to be the fastest in the middle. So it should look something sort of like this, right? Something where we reach a max speed at the middle. I don't know exactly what function it's going to be. Well, I do, but maybe we don't. But we kind of know at least the basic shape. Now what we're going to do is we're going to take the Navier-Stokes equations here, simplify them, and see what we can do. We're going to first describe everything that we know about the flow. We're going to use the same methods to be able to cross out as many terms as we can in the Navier-Stokes equations so that we can actually turn it into an easy enough math problem that we can solve. So the first thing that we're going to say about the flow is let's pretend this flow is steady state. It's not changing with time. That's going to tell us that the change in the velocity with time is equal to 0. So anywhere where we see a time derivative, like we do here and here and here, we know that that time derivative is going to be 0 because the velocity is not changing with time. The second thing that we know is we can look at just the direction of the flow. It's going to flow from left to right. That's what we've called the x direction. So we can say the velocity in the y direction must be 0, and the velocity in the z direction must also be 0. So this really does a lot of good work for us. I'm going to use blue. The velocity here, so there's a v, that gets crossed out. There's a w, that gets crossed out. Maybe you want to pause it and try this by yourself. Otherwise, follow along with me. So I'm going to cross out all the V's and all the W's, right? I can cross out derivatives too because the derivative of 0 is still 0. The second derivative of 0 is still 0. So I'm looking for all the V's and all the W's. So this really crosses out a lot of the X direction and Y direction, or the Y direction and Z direction. These last two equations, 527b and 527c, because our flow is simply not in that direction, so we don't have many terms left over from those equations. We can then say gravity, as we've drawn it, let's say that gravity is in the Y direction, the up and down direction, so that means that, right, gravity in the X direction is 0 and gravity in the Z direction is 0. Once we've crossed out almost every term but one, in this last equation, we know dp dz is also 0, and we've solved that last equation. So we have no pressure change in the Z direction. There's no difference in the pressure as we go in and out of the page. No big surprise. We also find that here, just like we did before, this just shows that P increases with depth. So in the Y direction, it's a fluid statics problem. We have higher pressure deeper down because we're deeper. Not a very interesting problem, but that's what the Y dimension is doing. The last thing that we know about the system is that our flow is left to right, but it's changing in the up and down direction in the Y direction. So du dx, we're not changing from left to right, so the derivative is 0. And the derivative in the Z direction, we're not changing in that direction, so that is also 0. So we're finding the derivative of u with respect to x, that one's 0. Second derivative, that one is also 0. This one is also 0. And then that's the end of the simplification piece. So we're left with most of the terms crossed out, but now a simple enough problem that we can actually solve it. So the pieces that are remaining are just this piece here and the pressure gradient. So let's write out this simpler problem and the boundary conditions. We crossed out everything again on the left side. Can zoom out so we can see a little bit. We crossed out everything on the left side, so that's a 0. We have minus dp dx, that's left over, plus mu d squared u dy squared. So that's our simplified differential equation. We have still two boundary conditions, boundary condition 1, boundary condition 2. We need two boundary conditions because we have a second derivative in y. Our two boundary conditions are going to be, if we zoom up, we can use the no slip condition. So we know it's going to be 0 velocity on the bottom and 0 velocity on the top. So velocity at the bottom is 0, and velocity here at the top also is equal to 0. This is our math problem. Now we can kind of dive in and solve it. So I've rewritten this math problem here. I've also highlighted here another possible option for boundary conditions. So boundary conditions are described at places where we know what the answer is. So we know here the velocity at, say, the bottom wall is 0. We know the velocity at the top wall is 0. That's kind of the boundary condition that we chose up here. But we could also say something about the middle of the system at y equals b over 2. So halfway across the channel, we know that it has to reach a maximum. So the maximum's not, say, closer to the top side than the bottom side. The maximum's going to be in the middle. That's going to be the place where we're farthest at the walls. So that would be the place where the derivative is 0. Another possible option for boundary conditions, it wouldn't change the answer. It would just change a little bit how we get there. So I would recommend pausing it now. See if you can't solve this differential equation along with the boundary conditions. Try your best and then jump back in with me and we'll solve it together. All right, so if you're back with me, we can start solving this. So I'm going to move some things around and get d squared u dy squared, and then I'll just have everything else on the other side. So 1 over mu dp dx. Now dp dx feels a little weird. That's the pressure gradient. In the y dimension, though, it's not a changing thing. It's not changing up and down. It's changing left to right. So when we actually try to separate variables, right, pretend we're multiplying both sides by dy, we have 1 over mu dp dx dy. We can just integrate this and treat that whole piece as a constant. So dp dx, it feels weird because it has a derivative in it, but in the y dimension, it's a constant. So this is 1 over mu dp dx. That whole piece feels like a constant. So that just integrates to y plus an unknown constant, c1. We can do that again. So now we have a little bit bigger equation. Partial p, partial x, y plus c1, all times dy, and then we integrate that whole big mess. Integrate kind of each part separately. The first y integrates to y squared over 2, so that's going to be 1 over 2, 1 over mu dp dx, y squared, and the second one integrates to c1y plus our unknown constant c2. Now we apply our boundary conditions. So our first one is that we're 0 at the bottom. So we can plug that in. 0 equals 1/2 1 over mu dp dx. You maybe can see what the answer is going to be, but we'll just do it all out in longhand. Then we're going to solve this equation for c2. So we plugged in 0 for y, we plugged in 0 for u because that's what our boundary condition said, and this says that c2 must be 0. Our second boundary condition is a little more interesting. So this says that the velocity at b is 0. So we plug in 0 for u, we plug in b for y, dp dx. So now we have b, wherever y was, plus c1 b. A little bit harder to solve, but we can solve this for c1. Right, not really too bad. So c1 must equal negative 1/2 1 over mu dp dx b. Now we plug that value of c1 back into u, and we can get our answer. Because they both have this same kind of jumble of constants out front, I'm going to pull those all out front. So 1 over 2 mu, maybe I'll even put the dp dx on top, 1 over 2 mu. And then our, we simply have y squared minus y b. That is our flow profile. So a nice simple parabola, and we actually get, right, this looks sort of like ones that we've solved before, but here we can see the max speed. Here this would be like max speed is dependent on both viscosity and pressure. Maybe not that surprising. The max speed that you get cares about what's that pressure gradient, how much higher is the pressure on the left side than the right side, and what is the fluid viscosity. So join me back again for one final example. in the next video.